Hi friends, in this video we'll discuss about the evaporative cooling effect inside a pot which is filled with water. So maybe I'll just take a reference here. So you can see if this is the pot which is filled with water and this is the pot thickness. This is the pot thickness and this is a porous media. So the thickness of the pot is a porous media which is filled with water, and of course inside is also completely filled, it is water. That is a fluid media and this is a porous media. In the porous media, so that is filled with both sand as well as porous media, or clay and water. I can say clay plus water. So if I try to zoom this particular area, I'll draw it here. So this is water and here clay plus water. Clay plus water. And the water tries to seep over this porous media, and it comes to the surface of the pot and it checks for the adjacent cell, which is air plus water vapor. And once if the saturation pressure at the temperature surrounding it, maybe the temperature surrounding it, if it is T surrounding, if the pressure present in that cell at that T surrounding temperature, if it is at that saturation pressure, then the water will not convert into water vapor. But if the pressure present in this cell which is adjacent to pot is less than the saturation pressure, then the water will try to cross this interface and turn into water vapor, and it will go into this adjacent fluid cell. In order to go in that way, the water will lose its latent heat in the form of vapor, or it will tries to relaxes its latent heat in order to convert from water to water vapor. So the heat required in order to convert water to water vapor is taken from the adjacent cells, or maybe we can say this way, the cell which is present just beside the clay pot, the temperature would drop because it loses its latent heat as HFG, and the water will turn into water vapor. And this happens until the adjacent cell is completely filled with water vapor. But the clay pot is present in an infinite atmosphere. As once the water vapor is filled here, so this enthalpy would increase due to the presence of water vapor, and there is a transfer of this water vapor due to the pressure difference or density difference, because this is now at a lower density and it travels to places where there is a which is having a low concentration of water vapor, which has a low concentration of water vapor. This part traverses, and now fresh air will come. Now fresh air will again have a low water vapor. Again this process repeats, it goes on until the temperature will reduce until a certain level, right? So this is the process of evaporative cooling that we actually see in all the clay pot which is filled with the water. Now as the temperature drops here, so what happens? The water would be at a higher temperature. There will be heat transfer from water to this part, and the temperature will drops. So the water temperature also obviously will drop as the latent heat is removed and it is transferred in the form of water vapor to the adjacent air media. Okay, so the amount of mass transfer that occurs from water to water vapor is defined by m dot is equals to hm into a naught into rho vw minus rho v infinity. So rho vw is nothing but the water vapor pressure present at the location, and rho v infinity is a, or sorry, it is density of the water vapor, and this is the density of the water vapor at temperature T infinity, and this is at the saturation temperature. It's nothing but, so what is the amount of water vapor? So rho vw is nothing but pressure of water vapor at Tsat, or at any temperature. For time being it's any temperature, and this water vapor is saturation water temperature or saturation water vapor pressure divided by RT, right? But at rho v infinity it is nothing but P at that particular temperature, RT infinity. Okay, so this is the pressure which is at saturated condition, it's at a normal ambient condition. So this is the driving force for the water to move from clay pot to the adjacent ambient air. Hm is the mass transfer coefficient and A naught is the surface area. As you can see, this surface is split into many small phases when you try to define it with a discretization, I mean mesh. In ANSYS Fluent or Star CCM Plus, for time being it can be any tool of Fluent or CFD, I mean any CFD tool. So it will have some A naught as a surface area. From this surface only it tries to remove the water and it turns into water vapor. So that is that A naught. And HM would have a units of meter per second. A naught would be having a units of meter square and density in the kg per meter cube. So totally will be getting kg per second as the unit. And when you try to define it in any ANSYS Fluent UDF, so you need to divide by the volume of the adjacent cell to the clay pot. So in order to get the unit of kg per second per meter cube, which is the unit that need to be given to the mass source of ANSYS Fluent. And obviously this Hm, which is the mass transfer coefficient, is a function of convective coefficient Hc, rho, specific heat, and Lewis number. Lewis number, again, this is a formula how you can calculate the mass transfer coefficient. And whereas Hc is the heat transfer, convective heat transfer coefficient that can be found from any of the CFD tools. Right? In this way, you'll be getting the mass that is been transferred from the clay pot to surroundings. Right? And once you get m dot, obviously the latent heat or the energy that is removed from the clay pot is nothing but m dot into hfg. Hfg is the latent heat of vaporization. So now maybe we'll just go through the Fluent interface, how it exactly look like. So this is the pot, and of course there is a surrounding atmosphere also. I'll just show you. Maybe I'll just show everything. So this is the surrounding atmosphere, in which I have considered only to represent this is the pot. Okay, so all these faces what you're seeing on the screen, small faces, are nothing but A naught. From that faces only the water will go and seep into the atmosphere. Okay, so it's nothing, a simple setup. Minus 9.81 gravity in the transient phenomena, so laminar flow I have taken, and it is a mixtures. In that I have taken a mixture template, water vapor plus air, and in the water it's a water liquid. Right, I have created this mixture by turning on the species transport. After turning on the species transport, I have created this mixer template, which in one mixer template, the names are water vapor and air. The density as volume weighted average I have taken. These are the properties. And in another one, I have created the water mixture. Only simply water is present as a species. Then in the mixture, I have taken one phase as vapor and air mixture, and other phase is nothing but water. For primary phase is water, and the secondary phase is mixture template. The phase interaction between phase 1 and phase 2, there is surface tension coefficient which I have taken, right? And then so there is no mass transfer model here. Maybe I'll just show you that UDF what I have selected. This is a UDF what I have selected. So as I stated, at the adjacent face, I have created this. This all the stuff it is used in order to find that raw water vapor and the raw saturated. So these are the 2 points what I've calculated. As I mentioned, these are the important points for the densities. And now I have taken HM, heat transfer or mass transfer coefficient with a constant value 0.019. That is generally for a natural convection. So I've taken that as a constant value, but it should be actually calculated using this formula. If anybody will require help how to calculate this, I can help them out. You can just drop a mail to the mail ID what I mentioned in the section. And this is the 0.019, and this area is nothing but the face area, individual face area, and the difference between the densities across that area. And this is for air, so air will have the addition of that mass, so I've kept it positive and I've used the user defined memory for that in order to store. And for water, that is negative because water will lose that mass. And of course there is another term which is multiplied with the hfg in order to have that energy removed from the water. So that I have done here and I've stored in the user defined memories. And with respect to the respective source terms, I've used the mass source liquid and energy source. So in the energy source and mass sources, I have divided by volume because everything should be in the units of per meter cube. That's the reason I have divided by C underscore volume C comma T. So this is a simple UD of what I have written in order to have the same methodology what we have discussed in the previous slide. So and after that you just need to go to this, and of course this is an out pressure outlet. Turn it into the pressure outlet, or you can just set a pressure inlet, you can just convert. And with temperature as 300 and phase to the species, the water vapor species, nothing but 0.008. So this I have considered as the water vapor 40% relative humidity I have considered. These are H2O fraction, and this is the completely backflow fraction or the volume fraction at the inlet would be 1. So this is nothing but the external surfaces of the wall what you can see here. Maybe I'll just show you. So all these faces, what you're seeing in the blue color, those faces I have given the pressure inlet, and with the respect to water vapor species as well as the entire multi-phase fraction for them is 1, because that is the only thing that is entering here. There is no water liquid coming from the outside the outlet into the outlet, right? And after that you can just do initialize. And yeah, sorry, before that we need to have that compilation of the UDF. Forgot, I have already written that UDF and I've already compiled it. And then after compiling it, there is a porous media also which need to be given to the pot thickness, right? So the pot thickness also we have considered with point 1 as the porosity value, very low porosity, because sorry, point 0.04 I've considered for the porosity. I'll just show you one second. What is the value I have considered here? Is for porous. So okay, let's say 0.05 is the porosity value what I've considered, and it's a clay material. You get the properties by searching out using any chat GPT. And the source terms what we need to add to the porous fluid is the energy source, because we need to remove the energy from the adjacent face of the pot which is open to atmosphere, and in that there's a phase one which is water liquid. We need to add one source term which is mass. We need to remove that water from that surface, and we need to add that as a water vapor to the surface or to the cell of the air which is adjacent to that surface, right? In the porous zone, this is a simple calculation of viscous resistances. You will get the inertial resistance and viscous resistance formulas and directly calculate that, and I've integrated into this. And the phase two, there is a water vapor that should be added, right? So that also I have added into the source terms. So yeah, you should add here. In this, there will be two source terms: water vapor source term and water liquid source term. Sorry, vapor source term. Both source terms should be added into the adjacent faces of the. So these additions would nothing but replicate the addition here. To these cells, the source term should be added, and the removal from the water part of the clay would be removed from here. So if I draw here, so this is the clay interface. The addition of the water will take place here, and removal of the water would be taking place here. So addition of the water means addition of water vapor, what I mean to say. This is the removal of water. And here also there is a removal of energy, right? So there are three aspects what we need to consider: removal of energy, removal of water, addition of water vapor. Then after you can just initialize. After initialization, we should patch with the pot. I'll just show you. There's a two parts what I have created. One is inner internal bottom part, internal top part. Internal bottom part has the water, and internal top part has air plus vapor, and the external part is completely vapor, and the pot thickness is filled with clay plus water, so that should also be filled with water. So now if you can take phase 2, this should be 0 for internal fluid bottom, and the porous fluid, these should be 0. It means it is filled with water in these two regions. Pass that, and then you can just verify the counters what we have taken. So this gives the velocity fractions of the entire stream. You will not see any velocities initially, and after running you can just see, and this is the temperatures of the region, the pot, right? This is the temperatures of the pot, and uh, we have this as the time step size, and I'll start calculating. Maybe after some time I'll just show you that counters how it look like. So now you can check here. So these are the velocity magnitude, how it is varying with respect to time. So I have recorded those animations, and I'm just playing it on the screen. You can see. So the velocity is happening at the interface of the clay, because there the water will be turned into water vapor, and water vapor mass will be added into the surrounding air. So that's the reason why you see velocity at this phase, right? And I also recorded the temperature variations. You can see the temperature variations also. The temperature variation, of course, I have ran for only 85 seconds. If you run for more amount of time, you can see more variation in the temperature. Now you can see in this area the temperature is reducing. In this part also temperature reducing. If you are on more amount of time, so you can see a significant change in temperature. So now the entire red color is turning into green, and it will turn into more at lower temperature blue, and of course it will turn into more and more lower temperature. Okay, hope you have enjoyed this video. I'll share the case file in the comments. You can, sorry, in the description. You can just take the case file if you require. Thank you.